In this video, we're going to look at a few more examples of the basic comparison test. Prove that if an is larger or equal to 0 for all n bigger or equal to 1, and summation n equals 1 to infinity an converges, then the summation n equals 1 to infinity an squared also converges. Now, we know that summation an converges by assumption. N equals 1 to infinity, summation an converges. And this implies that the limit of the nth term as n goes to infinity is equal to 0. Now, since the limit as n goes to infinity of an is equal to 0, then for sufficiently large n larger or equal to capital N, an, the nth term, will be less than 1 because it's approaching 0, so eventually it will be less than 1. And since an is less than 1, larger or equal to 0, then an squared is less than or equal to an. Why is that? The reason is because a fraction less than 1 squared is less than the original fraction that we started with. I'll repeat that. A fraction less than 1 squared is less than the original fraction that we started with. So, for example, 1/2 squared is equal to 1/4, and that's less than 1/2. A positive fraction squared is less than the original fraction that we started with. Now, since an squared is less than or equal to an, for all n large or equal to capital N, and we know that summation n equals capital N to infinity an converges by assumption, then summation an squared n equals n to infinity also converges by the basic comparison test. And since adding or subtracting a finite number of terms from a series does not affect the convergence-divergence of the series, we can conclude that summation n equals 1 to infinity an squared also converges. So because adding or subtracting a finite number of terms from a series doesn't affect the convergence or divergence of the series, we can start the index at n equals 1 and say our original series n equals 1 to infinity an squared also converges. And it converges, of course, by the basic comparison test. So let's summarize. An squared, every term of our given series is less than or equal to every term of the comparison series for small n larger or equal to capital N. This implies that the sum of our given series is less than the sum of our comparison series, which converges by assumption, is less than summation n equals capital N to infinity an. And on the right-hand side, this is a convergent series. So therefore, summation an squared n equals capital N to infinity converges by comparison test. All right, let's look at another example. Does the following series converge or diverge? Here we have summation k equals 2 to infinity, 2k divided by 4k minus 2 to the power of k. Intuitively, we know that 2k divided by 4k minus 2 to the power of k is going to be approximately 2k divided by 4k, because this minus 2 doesn't affect the magnitude of this ratio. For large k, that is, we can just ignore the constant minus 2. And the k's cancel out, and we get 1/2, so these k's cancel out. We get 2 over 4, which is 1/2 to the power of k. This is for large k. Since our given series summation k equals 2 to infinity 2k divided by 4k minus 2 to the power of k behaves like it's approximately equal to summation k equals 2 to infinity 1/2 to the k, which is a convergent, this is a convergent geometric series with common ratio of 1/2 less than 1. So, which is a convergent summation k equals 2 to infinity 1/2 to the k, 1/2 to the power of k, is a convergent geometric. Why is it convergent? Because the common ratio is equal to 1/2. Absolute value of r is equal to 1/2, which is less than 1. So intuitively, we know that the given series that we have also converges. So the given series, k equals 2 to infinity 2k divided by 4k minus 2. Intuitively, we feel that our given series also converges. But of course, we have to formally verify our intuition by applying the basic comparison test. So this is just developing the intuition. Now we verify the intuition. All right, so let's formally verify our intuition by applying the basic comparison test. Our given series is summation k equals 2 to infinity 2k divided by 4k minus 2 to the power of k. Now we know that k is larger or equal to 2 because the index starts at k equals 2. Multiply both sides by minus k. We get minus k is less than or equal to minus 2. Now, we have minus k is less than or equal to minus 2. Let's add 4k to both sides. Add 4k. So we have 4k minus 2 is larger or equal to 3k. We have now constructed the denominator of our given series. So 4k minus 2 is larger or equal to 3k. Flip both sides, reciprocate, we get 1 over 4k minus 2, and the inequality changes direction, so we get less than or equal to 1 over 3k. So now raise both sides to the power of k, and let's multiply by 2k as well, so we get 2k divided by 4k minus 2 is less than or equal to 2k divided by 3k. Now raise both sides of this inequality to the power of k. So we have 2k divided by 4k minus 2 to the power of k is less than or equal to, and these k's cancel out, so less than or equal to 2/3 to the power of k. Now you can see we have constructed a general term of our given series. So we have 2k divided by 4k minus 2 to the power of k is less than or equal to 2/3 to the k. What do you notice about 2/3 to the k? This is the general term of a convergent geometric series. Let's write that down. Summation k equals 2 to infinity 2/3 to the k is a convergent geometric series with absolute value of r is equal to 2/3 less than 1. That means the given series that we have, summation k equals 2 to infinity 2k divided by 4k minus 2 to the power of k also converges by the basic comparison test. I'll just say comparison test. Comparison test. So let's summarize. Here's our given series. K equals 2 to infinity 2k divided by 4k minus 2 to the power of k. and we prove that every term of our given series is less than a comparison series, which is a convergent geometric series with common ratio of 2/3, which is less than 1. Summation k equals 2 to infinity, 2/3 to the k. Every term of our given series is less than every term of the comparison geometric series, which is a convergent geometric series because the common ratio is less than 1. Convergent geometric series with common ratio r, which is equal to 2/3 less than 1. And for this reason, our given series summation k equals 2 to infinity, 2k divided by 4k minus 2 to the power of k, our given series converges by the basic comparison test. All right, thanks.